Hi, welcome. I'm Andrew Jones. I work for Ventana Microsystems. And today I will be talking about the RISC-V software ecosystem. Before I even put up my outline, trust me, I have one, but it's deeper down. I wanted to actually point out what probably most of you here already know, and that's that the RISC-V community is making a lot of ISA extensions, and they're making them fast. I've even had people tell me that we're creating like an alphabet soup because of the single letter ones anyway. And so this graph just shows you that over the last 5 years, we've been having tens of extensions ratified every year, and we're on track to do even more, right? And so I'm not really surprised that with that kind of rate of ISA ratification, that people had been saying, or articles had been showing up, that, well, there's just no way the software ecosystem is keeping up, and so the long pole is now the software ecosystem. We need to get the software ready. You got to get the software ready. It's not ready. And so one of my motivations for this talk was to kind of change that narrative a little bit, because I think we're actually doing pretty well. And for any of those who've been going to the same sessions I have anyway, I think you'd agree, because over the last couple of days, I've been hearing that from basically everywhere at the summits, including the members-only days on Tuesday. So we're not hearing that anymore, and I guess my job is done. And see you guys later. No. Thanks. Here's just an example of one of the quotes I extracted from a recent article to point that out more specifically. This one's tool chain, compiler related. I'll be speaking more about operating systems because that's the kind of work I do. Okay, so finally the outline I promised. How is software keeping up? How do we know it's a healthy software ecosystem? I mean, we could be keeping up, but just kind of a junky, fast thing, right? Move fast, break stuff. Specifically what ingredient, and in that bullet, we'll talk specifically about some of the ingredients we need for a healthy ecosystem. And then we'll elaborate more on specifically the profiles, RVA23, then into my domain, which I know more about, what we're doing in Linux and KVM for that. And finally, some suggestions for the ISA extensions of the future, because we do see some gaps. Don't get me wrong, RISC-V is awesome, but we have some improvements. It's an iterative process. Okay, so how are we keeping up? Well, how is it possible to keep up with all these extensions ratified per year? Well, one thing is we have a lot of people working on software. It's an open source effort, and so we lean on each other. Companies, competitors, it doesn't matter. We all work on the same software together. And even people who aren't necessarily looking to enable RISC-V, so they could be working on x86 or ARM, whatever, we're sharing code with them, right? We have shared components that is architecture neutral. And they also want to enable the best code they can, so they need to consider different perspectives, different architectures, and so they're contributing too. And so how do we manage all these different people we have trying to contribute to similar or same problems, solving similar or same problems? And that's RISE. I don't know, I assume most people here already know about RISE. And if you don't, in 1 hour, I think in this room, there will be a talk specifically on RISE that I encourage you to come to. And so this is a group, RISE allows you to get proposals for things that we think we need to do in the software world for RISC-V, as well as help steer the work being done down the same roads, make sure there's no redundancy, things like that. And so this is a great way to coordinate the efforts. Another reason why software can keep up with ISA extension development is because we don't actually need hardware right away. We have emulation for that, right? And so in fact, we have an open source emulator that probably everyone in the room knows, QEMU, something I work on myself. We add extensions there very easily. We can even get extensions merged, extension support merged that hasn't been ratified. So these are just draft versions of an ISA extension out there, still going through iteration, still being developed. And we can go to QEMU with a model that works for that particular draft version, and get it merged flagged as experimental. So that means don't count on being there next year or ever. It could get ripped back out. But the fact that it's there merged into the code base allows you to share that among the community easily and integrate it with other extension support easily. And then for some components, and I'm thinking of Linux here because that's what I work on, but there are others I'm sure as well, there are actually frameworks built into the code that allow you to start exploiting these new extensions that have new instructions even before the tool chains do. Because, I mean, many things will want to wait for a tool changes to compile it and use it. But Linux, for example, we have a framework where we can do instruction definitions, so you can prepare to use them in advance, and then you can use them with an alternative framework, et cetera. And you don't need the tool chain involved in that. Finally, we kind of have to have the software ecosystem keeping up with the ISA extensions. I don't believe it's a hard requirement, but many extensions want to do some sort of a proof of concept. So they build out a software stack that probably includes Linux and some application or whatever in order to show that when they try to realize that ISA extension that they're designing, it actually does do what they thought it was going to do. There wasn't a gap there that they hadn't thought of that came out about after trying to implement support for it. And so, yeah, just the fact that there are at least RFCs on the mailing list for software support for these types of things before the ratification of the extension is done means that the software is being worked on in parallel. Okay, so how do we know an ecosystem is healthy? And yeah, that is a picture of a frog. I didn't know how to draw a software ecosystem. So I had AI draw me a picture of an ecosystem, and there you go. I'm pretty sure it's a healthy ecosystem because the frog looks happy. Now, what do we do? How do we know if a software ecosystem is healthy? Well, it has to have the components of any generic healthy ecosystem, and that's that all the parts of it need to work together, right? And for software, that would be certain protocols or formats that are shared. Different functionalities can be shared, libraries, et cetera. And maybe every component has its own selfish goals or its own purpose, which it feels are unrelated to everything else in the ecosystem, but they end up overlapping quite a bit, these goals, right? So they work together. That's what a healthy ecosystem looks like. So how do we make sure that the RISC-V software ecosystem is aligning its goals and sharing? And we do that the same way we do with the RISC-V ISA world, the actual hardware. We do a common effort by specifying what it should look like. And so we have specifications for software as well. These are actually all done under RVI, just like any ISA extension would be. The first one on the list there is actually right on the boundary between hardware and software. It says what a platform should look like, what software can expect the platform to have. And then the software side is like, okay, I can expect the platform to have that, so I should be prepared for that. And so that's a nice way to coordinate efforts to make sure that the software ecosystem will just boot on your platform. Is both hardware side is conformant to the server platform spec and software as well. And to do that, we have people from both sides. We have hardware vendors and operating system vendors in the same room together saying, hey, I really would prefer this to be there, can be there, and then the hardware guy says maybe yes, maybe no, and then it all gets hashed out, right? And so these other two specs here, boot and runtime services, are similar. They tell you what kinds of things to expect for your boot flow, what kind of runtime services will be there after you boot up. So we kind of focus our software down a certain road that way. Same goes for the SPI, which is explaining which is specifying how your in mode will respond to different service requests. And then the final one there on that list is that the one that I will talk about more, the profiles, the RVA23 specifically. And what that one is it says, hey, this collection of extensions is going to be present, so you can go ahead and compile for it. Finally, one more bullet on what makes the software ecosystem healthy slide is the fact that we're working on upstream open source projects for the most part for RISC-V. So this is actually a great way to keep a software ecosystem healthy. We have, as I said, with the RISE comment in the previous slide, We have everyone working together and trying to achieve the same goals. And so when we get it upstream first, it can be shared and built on top of, right? We don't have one fork here doing the same thing 2 different ways and then not being able to communicate among each other. We actually put everything upstream and everybody gets from there, they share and they work together. And this is great for the distros too, of course. So they can just go ahead and pull down all these upstream repos and package everything together. And you get all the good stuff in one place, and then users can easily go grab that distro and adopt it. Okay, so we have healthy RISC-V ecosystem, and one of the components I mentioned that helps us do that is the profile. So we have this profile specification, it's got its own TG, it's working to decide what we would like to see mandated for extensions in order to make sure that we can compile and be useful with our software. And so this is the RVA23 ISA string, just a couple of characters there, easy to read. But one of the things you want to see there is that, yeah, you've got stuff in there like B and V, so you can actually expect these extensions which bring in instructions allowing optimized routines that you need for a competitive software. And they're already there, so go ahead and build for them. You don't need to have any overhead associated with detecting that they're there and then enabling them or anything like that. You just get them. And that's what helps. Now, there's a trade-off. If you start building your software for that string, you expect platforms to have that string, or it's not going to work. Your binary will break. I think this is going to be okay in the long run. I mean, because what we're doing now is we're creating these classes, these profile classes, and we still will allow software to freely work on any platform in the class. So they're interoperable. They're still interoperable among a class, and that's the plan, and it looks good. Okay, so far I've been just talking about how we're there, and now I want to switch gears a little bit and make sure people understand how the software I'm working on is working in regard to maintaining this healthy ecosystem. So in Linux, it's aware of what extensions are available because it's hardware description, whether that be ACPI or device tree, tells it what's there. And then it needs to expose that information to the user space in one way or another, so it's aware of what's there, at least for the optional extensions. Remember, the profiles you build for it, and it will be there, but optional extensions are still something we want to be able to support, and we need to be able to pass that information along. I think I got these bullets a little bit out of order because the most important bullet is that third sub-bullet down, extensions that do not need kernel support are still advertised. And the standard way to find out about them is this hardware probe syscall on Linux. So Linux provides this thing, and we want applications to start adopting this. I think a little more momentum needs to be pushed here, more awareness of how that works, and start using it more. But that's the plan, and that's what we're going for. Applications that need to use an optional extension should use hardware probe to find out if it's there, and then they can use it. The thing is just a simple key value system call. You put in, hey, do I have atomic compare and swap on this machine? And it comes back yes, no. There are a couple of things to keep in mind, like the fact that it is possible to have later kernel headers in your user space and running some old kernel for whatever reasons. And then you're going to get a negative result, potentially an ambiguous negative result. It could mean that, okay, the older kernel didn't know about that, even though your kernel headers say it does. Or it could mean the platform doesn't support it. No way for you to know. That's kind of a corner case, so I'm not too nervous about it. Maybe the bigger deal would be that neither the kernel headers nor the kernel are aware of a particular extension. And that can hold up user space adoption because it goes checks hardware probe and it says not there, even if it is. And I think we're doing a good job keeping up in the kernel community. If there's something missing, though, just tell us. We'll get it in there quick. It's not that hard. Okay, but what about the use of extensions in the Linux kernel? We also want to do that, of course, too. For the time being, everything is an optional extension. At some point, we'll probably also want to start considering profiles, and you can say, the profile extension is present, and now you have all that stuff just to help reduce all the management of each one individually. But we're not there yet, and it's not really a priority. Being able to manage either a single profile bit or a whole bunch of bits that mean the same thing is pretty much the same thing. Being able to enable the optional extensions is important, of course. You can't compile for them directly. You need to be able to detect them and run them, but Linux is able to do that quite well. It has a framework built into it where at boot time it detects the presence of an extension, and then it goes and does some kernel patching, runtime kernel patching, so you can actually use the instructions of that extension with no branching. You don't have a branch above every time you want to use that instruction saying, hey, do I have it or not? No, it just knows it's there after booting up. KVM-wise, what's important there? Well, the guest kernels, everything I just said is the same. But KVM is now a platform. So we kind of switched things. We've been talking about what software needs to do with respect to understanding what platform devices have. And now we're saying, hey, software is the platform producing the ISA for the guest kernels. And so it needs to look at things a little bit differently. This is just showing a flow here, how the user and the virtual machine manager, they need to decide what they want to expose to guests. They need to coordinate with KVM to see if it's possible. And then they want to configure precisely that for the guest, nothing more. That brings me into the final phase of this. So what can we do maybe for improvements over all of this? That was a should in the last slide, that they should be able to do that. They cannot at this time. We have a lot of behaviors in RISC-V extensions, particularly ones that have CSRs, that say, hey, this field is a WORL. WORL means write anything you want, but you'll read back only legal values. And anyway, the fact that this behavior can be different on different platforms will cause migration issues. If I boot a guest and there's like 3 different variants of legal values on there, and I pick one, but then I go somewhere else where there's only 2 variants and I'm using the wrong one, it's not gonna work, right? So I need to know that I'm not gonna do that before I do the migration. And any other behavior has the same sort of concept. We need to name these behaviors. The profiles group is doing a good job of that already. We need to stop doing some of these behaviors as well with new ISA extensions, and then we'll be able to achieve better support for live migration. Also, we would like to be able to shut off all the extensions that we don't want to show, because even though I'm telling everyone to use your hardware probe to see if it's there, well, yeah, sure. What if I just use the instruction without checking first and it worked? It works. And same goes for guests. If the hypervisor says, no, you don't really have that extension, but it's just trying to pretend it doesn't exist, and then it tries to use it, well, it's there. It would be nice if the hypervisor could actually turn it off so you get an exception instead of be able to use it. And performance shouldn't have to be a major trade-off in those designs either. We should be able to turn something off without having to say, okay, you're just going to trap and emulate everything now. All right. I'm already a minute over, sorry. I will just basically show you the summary slide because I don't have anything to add to it. These are the main points. I wanted to point out we are keeping pace, at least in my opinion, with all the ISA extensions. Profiles are the way to go. Linux KVM support, RVA23, and when hardware is available, will be good. Yeah, use hardware probe, and let's think about live migration in the future.